Hey everyone, welcome to Unit 30. This is going to be the DC generators. And in this lesson here, we're going to talk about how to create electrical energy from mechanical energy. So, this device we're going to talk about today is basically that's its one purpose is to change that mechanical energy into electrical. We got to figure out how that happens and why it happens. So, the first thing we're going to talk about is going to be what is a DC generator and the parts within it. So the parts are going to be your magnetic field, and then it's going to be your windings. All right. So there's two different main components that we need to talk about, and then the individual components that make up what it actually is. So the first part is going to be let's talk about a wire. What is a wire? All right. So a wire is a conductor. A conductor is a material that allows electron flow. So on the atomic level, we're going to see that materials that are considered conductors are going to have 2 to 3 valence electrons. Valence electrons, again, are the ones that are on the outside of the outermost orbit of that atom. They have 2 to 3 valence electrons. They can easily accept and give up their electrons with very little energy, respectively. An insulator, by the other means, is going to be something that has 7 or 8 valence electrons. So it has no room for anything else to come in, and it doesn't want to release anything very easily. So it has the ability to kind of bounce off electrons. Electrons come in and it just kind of bounces them off. It doesn't want to accept them or bring them into its orbit. An insulator is something like rubber, glass, plastic, things that just don't take electricity very well. Right? Not that they won't take it. With enough energy, anything will be penetrated with electricity or current, the atomic, at the atomic level at least. With a conductor, though, a conductor is again that material that has the 2 or 3 valence electrons, so it has the ability to accept it very easily. So these are like copper and iron, aluminum, metal, that kind of stuff, right? Things that easily that you would think of normally that would be a conductor. People mostly sometimes people think that water is a conductor. Water is not a conductor. Water is actually an insulator. The stuff in water makes it conductive. Salts and minerals and metals and things that we normally would consider water without being pure water is things that make it conductive. The water itself is not. So pure deionized water with everything removed is very corrosive and is very much an insulator. So people don't realize that as much. So the other part of this whole process is going to be the magnets. So the magnets come in two different flavors, right? One is going to be a permanent magnet, and one is going to be an electromagnet. A permanent magnet is a magnet that always has its magnetic field. Electromagnet requires current from a coil to produce that magnetic field. On the permanent magnet side, this could be a lodestone. This could be a neodymium. This could be something that would have that ability to always maintain its magnetic field. So refrigerator magnets and very strong toy magnets and big industrial magnets. Those are permanent magnets. They require no external power source. On the other hand, we have electromagnets. Electromagnets require the external source in order for it to produce a magnetic field. How this works is with any conductor, when you run current through it, current being from another source, so another source has energized and started moving these electrons through the wire, the current is flowing. As a current flows, it creates a magnetic field around the wire. So like the thing, and that magnetic field is called flux. The stronger the magnetic field, the tighter the flux, the more flux lines we have. The weaker the magnet, or the less current, the weaker the magnet, which makes less flux lines. So that one wire is not enough to produce any sort of magnetic field that is going to be worth using. So we have to magnify that. And how you magnify a magnetic field with an electromagnet is to wrap it many, many times. So you create a coil. You take that one piece of wire and you wrap it many, many times over and over and over, and that creates the electromagnet. Every time you add, it doubles. It gets stronger and stronger and stronger, um, making more surface area, making more magnetic flux, because each wire is now producing flux. So that's how you would create a electromagnet. Okay, so now we understand magnets and electromagnets, and now we understand what a conductor and insulator are. So let's go to our first picture here, and we're going to see this object here is going to be a device called a generator. So it has two main components. The inside is the armature, and the outside is the field. The field is a magnet, so it can either be permanent magnets or an electromagnet. Right now we're going to say it's permanent magnets, so no external water or source of energy. The internal is going to be the armature. The armature is going to spin within this magnetic field, and we're going to see what happens when that occurs. So the green block you see in the picture is going to be your armature, the frame, the base, the core, and that black line you see going around the green box is going to be your conductor, right? Now, when a conductor moves through magnetic flux, it's called cutting the flux. As you move through the flux, it excites the electrons in that copper wire. So as the wire moves from one point in space to another point in space, it has to rotate and cut through the flux. As it cuts through the flux, it excites the electrons and moves it to, it creates current, creates path. So the faster we rotate, the more we're cutting flux, the stronger the magnetic fields, the more flux we cut. There's a lot of different parts and pieces that will increase the voltage, and you'll see us as we go along. But right now, I just want to get you the basic concept. The purple boxes are your permanent magnets. You have a north and a south. Your green box is your armature core, and the black line going around is going to be your conductor. Okay. One other thing I want to show you before we move on is these little wheels here. The wheels are going to be the slip rings. Slip rings are basically a piece of steel metal. Could be copper, right? But they are solid. They're just a piece of wheel, a piece of material, and they are attached to the shaft. Now, the outermost part is the conductor. The inner part is non-conductive or an insulator. So it's not electrically bonded to the shaft itself, but it's mechanically bonded, so it will spin with the shaft. On the bottom of those slip rings, you're going to see these orange boxes, and that is your brushes. Your brushes are conductors, and we'll talk about those in a little bit, but the conductors are a material that allows you to send electrical signal through them while allowing slip and movement. So as the slip ring rotates, we're going to get contact. It's going to be contacting with these brushes, and the brushes will transfer that electricity to the stationary outer part of the generator. The rotation is not affected by any kind of wires or anything connected to the outside world because it's slipping. That's what they call the slip rings. It's allowing slippage, right? All right, so we got that part down. We know what the slip rings are. We know what the brushes are. The field pieces, the outer part, the field, and we want armature, okay? So the first thing we're talking about is how this works. So in this diagram here, a couple things I want to explain before we kind of get too far into it. You see these little horizontal lines. The horizontal lines are basically an illustration of flux lines. Flux lines are not perfectly straight across. They're waves, right? It's an energy. It's a field. But for this illustration, we're going to say they're straight across, right? Those two dots you see, one on top and one on the bottom, are wire. So if you took a piece of wire, right, and you cut the end off and you looked at the nose of it, you would see the end, the round wire. That is what we're looking at. That dot is the end of that wire. The part in the center, the very center piece, is where it rotates, and that is your main axle or your main shaft, right? Everything rotates around that point. The purple things, again, are going to be your permanent magnets, right? The thing on the bottom here is going to be your graph, and they have a zero line, so anything on the zero line is 0 volts. Voltage, again, is potential, it's push, it's energy. So if we have 0 push, we have our 0. If we're anything that's a positive push, it's above. And if it's a negative push or like a pull, would be a negative, right? And anything linearly going that direction is going to be time. So if we stop time, you'll see a different effect. but we can't stop time, obviously, so everything is going to have a length to it, or be linearly dragged out. You'll see that as we go along. So in this illustration here, we've rotated 90 degrees, allowing it to cut through the flux, right? So we cut from the top flux all the way through the middle flux, and we allowed it to get to the strongest point of the magnet, which is the center. And within that, we've increased from 0 up to a higher voltage. So at this point here, we've created energy by cutting the flux and excited the electrons in the wire. So the electrons are excited, and now they're moving and they're being pushed in a direction. So we're creating this positive voltage, right? We're going to rotate once again, and you're going to see that now we are 180 degrees from our original position, but only 90 degrees from our last position. So we were side to side, and now we are up and down again. We are currently outside of the flux lines, meaning that we are not cutting flux, and we are back again at 0. Okay, we are not in the same position because time has moved. From the time it took to rotate from the first position to the second to the third, time has been moving the whole time. So that's why we get this increase to a max, and then decrease, and then back to 0. Okay, we're going to rotate 90 degrees once again, and that is going to put us in the negative. Okay, so that same wire that was up top, then it was cutting the south field, then it was out of the field, now it's cutting through the north field. So the north field is going to be pulling or creating this energy in the opposite direction. That is going to be, we're going to call it negative. So that is negative, it's pulling energy from the system, negative, right? And then it brings us down to the peak, and then we're going to rotate once again, bring us back to our home position of 360 degrees or 0, and that is going to be back to its original position or back to 0 volts, right? So now we're back to our starting position, and with what we just created was called a sine wave. So a sine wave starts at one position, it goes to a point in space, which is our highest voltage, and then we move down to 0, and then we continue down to negative, and then we go back up to 0. So we created this wave. If we were to have time stopped, you would see that line go up, and then go to middle, and then down, and then back up. But because time keeps moving, you're getting this wave, this motion. I keep calling out the degrees because that's important. Later on, you're going to see that when electrical is, especially when communicating with AC or alternating current, which is what we just created, you're going to see that the different points in that wave have a degrees associated with them. That degree is based on the way we produce electricity currently. We produce it through a mechanical rotation field. So a full circle is 360 degrees. So our wave is created by the rotation of our generators at power plants, right? So it means if it's coal plant, nuclear, steam, coal, hydroelectric, whatever, right? You are producing some kind of an energy, typically steam, turning a turbine. The turbine is spinning a shaft. The shaft is actually physically rotating a generator. So what we're seeing in this wave is the actual physical rotation of the generators at the power plant. Okay, so now that we kind of understand that part there, later on it'll make a little more sense, hopefully, that when I say something is 40 degrees out of phase or 120 degrees out of phase, you kind of understand that it's out of phase from the original. So if you go with 40 degrees to that wave, you'll see that that's where the new wave starts, and it's 40 degrees out of phase, right? So currently we have an AC, but generators don't create AC. They do by nature, like this one here, but we have something else that we have to add to change that. So the next thing we're going to talk about is called a commutator. A commutator is a device that is kind of like a slip ring, but it has the center cut out. So the center being basically a ring cut in half. We have one ring this time. We have a ring, we've cut it in half. So we have a top section and a bottom section, right? So one half of the wire is hooked to the top, the other half of the wire is hooked to the bottom, and they are electrically separated, right? So they're not making any continuity. It's not a full complete loop, it's an open loop. This way here, we can have a device like these brushes contact each pad, right, and complete that circuit. So as the energy is being rotated or the flux is being cut as it goes through these magnetic fields, you're going to start seeing that you have this energy being produced, and we are still able to transfer the energy to the outside world, the stationary world. All right, so let's show you how this works. We're going to start at the beginning again. This is the first diagram. We're starting at 0 position, right? So same kind of graph. We're going to rotate 90 degrees. All right, same thing. The red half of the wire is cut through the south. The south has energized and push voltage, and it created this positive peak. We're going to rotate once again, and we're going to get back to zero. So far so good. Everything's exactly the same, right? So now we're going to rotate once again. The red isn't going to the north, the purple coming to the south, and we're going to go negative, right? No. The reason is because the commutator is a mechanical switch. And if you look really carefully, the part that is on the positive, you see the wire with the red wire with the positive plus sign, that is always contacted to whatever coil has gone through the south field. South field in this case being what's creating the positive energy. So if we have the original part, and we'll go back, you see the original part, the red was going through the south field, creating that positive, right? The red came out, now the red went away, but look who's going through, the purple, right? It's going through the south field. So it's always reconnecting itself with whoever is going through a particular field. It's picking out a specific set of coils going through there. So we get this other pulse in the positive direction. Now we've created DC, or direct current. So current is going the same way. We continue our path, do our full 360 degrees. We're still using rotation and degrees because we're still dealing with a rotating field. But this here is creating those two peaks. So the first, when you fire at zero, or at 0 degrees, the first peak is 90. The second one is 180. The second peak is 270. And the last one is 360. So we've made one rotation, but we've never crossed the zero line. We've always stayed up. The problem with this design is that we're always pushing in one direction. So it's kind of lurching forward and stopping, and then lurching forward and stopping. You get energy and then nothing, and then energy and nothing. So that's not really very beneficial. Also, with one wire, we're not creating a lot of voltage. It's a little voltage, but it's not a lot of voltage. So what we do, by simply adding more wraps, more windings, we have more conductors cutting through the flux, increasing our voltage, right? Now we want to take out that lurching motion, so we go ahead and cut our commutator in half once again, and now we have 4 winding sets that are actually going through these poles. So at any one point, you always have a coil going through the magnetic field, causing it to always produce a voltage. So you're going to get these little ripples versus off on, less lurching, right? So it's going to be a constant flow of electrons. Okay, the part in the center is called the core, right? And this is the armature base. The shaft goes in the middle. The commutator base is locked onto this base, and the coils or the windings that we talked about are on top of this. So you see these little grooves in this little device. So that's where the wires lay. They would lay inside there, and as this thing would rotate, it would align those coils with the magnet, and it keeps everything nice and stationary. Here's a nice illustration or a picture of one that shows that you have your commutator. This is the part in the corner here, the copper looking thing with the lines cut in it. That's where the commutator, and those are the pads for the commutator. Beyond that is the core, and then you see the little red wires. Those are your conductors, your wire. Now, the reason they're red is because they have an insulator, like a resin on them. That resin allows the wires to lay together without electrically making contact. So electrons cannot pass from one to the other easily. If you put too much voltage or current, you could possibly blow through that insulator. It happens. But typically, just a nominal voltage would not be able to allow it to go through that because they're not electrically connected. They're laying on top of each other, but because this one has insulator and this one has insulator, they're just kind of sandwiched. That's why you can get so many wraps. If we cut it in half, you can see right away that how deep those coils go and how many windings are in each wrap. All right, so there's a couple different, 3 actually, ways to actually wire these the armature up, and it all depends on how you want it, what kind of output you want. So the first one here we're going to call is a lap wound. So lap wound is going to be a way to wind the armature in order to produce a lot of current, but very little voltage. So the armatures in a generator and motor are pretty similar, almost exact. So if you add electrical energy, you get mechanical rotation. If you add mechanical rotation, you get electrical energy. The same device. So this type of winding is used for something like a car starter. Low voltage, 12 volts, but hundreds and hundreds of amps to crank and start your car. This type of generator would produce a low voltage but very, very high current, so you can do a lot of work with it, a lot of energy. The next we're going to talk about is going to be our wave wound. Our wave wound is going to be very high voltage but very little current. So in our generator world, we'd say this would be like a hand cranked radio or a flashlight or charging a cell phone through a hand crank. That would be that kind of generator because it can produce a lot of voltage relatively for what it is, producing 5 volts in some cases, and very low current, milliamps. So you're not really doing a lot of work, a lot of current flow, but you're overcoming the potential of the battery and allowing it to recharge a battery or charge electronics in a radio or whatever you have to do to hand crank. Last one's called a frog leg. The frog leg is a combination of both. It handles decent current and a decent amount of voltage. So it's kind of like the middle. That is our general use windings for armatures. You can see here the armature is in the middle. This is the spinny part. You'll see our commutator. That's the copper, shiny copper looking, and that has the lines cut into the side of it. Each one is electrically isolated, so they cannot be touching. And the brushes lay on top of those commutators. So as the armature rotates, the brushes stay still, and they electrically connect to the windings that are rotating inside the generator. Now, from what you can see in this picture here, you see the brush holders, which is where the brush sits in. You see the giant spring. The spring is pushing pressure on there, and that is allowing you to keep constant pressure. If for some reason you wear your brushes down, because they are softer, you will wear your brushes down to a point where they're beyond their safe point. The springs don't have enough pressure anymore, and they're going to be allowed to bounce, and you get a lot of sparking and arcing. That's where you're going to see that blue spark comes off on the commutator. That's from that reason there. Also, a poor seating where it's not perfectly seated on the commutator, because the commutator is round, and typically you got our flat brush. So as it wears in, it'll eventually create that curve, or you do it before you install it. But just to understand that whole center part does rotate, and the part with the wires on it here stays stationary. The part the wires attached to is called the field. The field is the outside part. And if you're ever confused, the armature, it sounds like armchair. Armchair sits in the center of a house. Your field is the outside, which remains on the outside of the house. So if you want to say field, outside, armchair lives in the inside. That's how I keep in mind to allow you to realize who's inside and who's outside. So the spinny part is the armature, the outside is the field. This only works for DC generators and DC motors. We have different terms for AC. So now we're going to talk about the pole pieces. The pole pieces are the big chunks of metal on the field that do not rotate. They stay still, they stay with the outside of the generator. This is allowed, they're allowed to amplify the magnetic field of the electromagnets. So an electromagnet by itself, we talked about earlier, if you wrap it around something, it allows you to create an electromagnet. By itself, it's called an air core. Nothing's in the center but air, right? You can have wood or plastic or something in the center. But a really strong electromagnet has iron, and that's what these are. These are like an iron plating that allows you to have a very strong electromagnet, basically. It takes everything, takes all those electrons and it adds it. How this works is that it's a softer material like an iron, and it's allowed to, when the magnetic field is created, all of the molecules, the electron molecules, all line up in one direction. So you're essentially creating not only your coil, but the actual device, the pole piece itself, is actually becoming its own magnet at the same time. All right. Within this, you can create different types of windings. You can have the way they lay. You have a round type, and you have a square. Square, you can get more wires in, so that's why motors are getting smaller and smaller, because we're able to get more horsepower, more energy, more voltage creation out of a smaller unit versus older units were much, much bigger. You can see the area density. So a square versus the round wire allows you to have a little more surface area for a magnetic field. And this is a picture of a armature that has a square wire on it. Okay, so now we're going to talk about the windings on the field. These are field windings. There's two different types. You have a series and you have a shunt. Series is going to be your S1, S2. Your shunt is going to be your F1, F2. Series is going to be wired in series or in line, and shunt is going to be wired in parallel. So each one has their benefits. The series is going to have a thicker wire and wrapped less times around the pole pieces. Your armature is going, I mean, your shunt wires are going to have more wraps and a much thinner wire. So it allows you to have different control or different strengths. Each one has a different strength. So there's two different types again. All right. You can see the field windings here. They're wrapped in like this epoxy tape, and this allows you to have a very safe skin almost over the coils, so they don't get damaged. They don't get dirt and grease inside the coils themselves, which would short them all out. So this allows it to have nice and safe, but has no problem. The magnetic field has no problem going through. You can see here that little horseshoe shape at the top, or also even say an amble shape, and that is the pole piece. The part you see at the bottom as wrapped around is going to be your field windings, and the pole piece is sticking up because it's going to be riding really close to that armature. Not touching, but very, very, very close. Okay. This particular winding here is our series winding. So our series winding, again, is the heavier wire, less wraps around the pole pieces. And you can see that we go in as A1, we go straight into a brush. The brush goes into the commutator goes into the armature windings, and then comes back out on another commutator plate, usually 180 degrees off from each other. So one's on one side, one's on the other. It's going to leave, and it's going to leave as A2. Right? We don't see A2 in this drawing because they've connected them in the drawing, but you'll typically see A2. A2 will be connected to S2 and be under a wire nut together. They're just put under one solid wire, so you see it come right off the brush, and it leaves and goes right to the pole piece. It's very rare it happens. I've seen a couple motors that were internally wired just like that, but typically you'll see all wires come out. Now the pole piece has the series winding, and it's going to go all the way around. So it's a wrap on each pole piece, and then it's going to come out as S1. So in this particular motor, we'd hook up S1 and A1, rotate the armature, and that would allow us to have our voltage. The one benefit of a series winding is that we can create a lot of current and a lot of voltage, right? So we have a little more energy. It's a much more powerful design. The bad part is that it's not very good at maintaining. So if you put a very large electrical load on, it will start to dive down, and it's one of its weaknesses. So it can produce a whole lot of voltage, but for its size, for what it does, but it's going to start diving down once you add more electrical load, more light bulbs, more resistors, more stuff. When you're plugging things into it, refrigerators and plugging stuff into your generator, it's going to eventually pull it down and down. So it's not going to be efficient no more. You can see here, once we add a load, our current is coming from the armature itself. The armature is being mechanically rotated. It's going through those little black boxes, which are the brushes illustrated. We're going to leave A2, go into our S2 on the series winding. That little squiggly line, that is an inductor, right? Inductor is another word for coil. So a coil is going to be the coil we talked about earlier, the series coils, the field windings, and that's going to be leaving. So when we rotate the armature, we're going to produce a voltage by cutting the flux we talked about a few minutes ago, and we're going to be allowed to send out that voltage out into our load being whatever is plugged into the system. All right, the more load we add, the more it bogs down. So it's going to be you're drawing more from the system, so it's not being as efficient, and it will start to lose its production very, very quickly, of production of voltage. All right, so you can see here that our winding will, as we add electrical load, the voltage will start to climb because it's very good at producing voltage. But once it reaches saturation, it can't do any more, and then the load is going to take over, and it's going to start coming back down. So there's a point at which that series motor is beyond its prime, and it can't do anything else. It's going to start diving down. Okay, the next one's called the shunt. The shunt is essentially a parallel. So shunt is another term for parallel or a shorter path. So our series, the original one, it was a constant flow. We went in one wire, we went through the brushes, through the armatures, back out the other brush, through the windings, and back out the motor or generator. So this one here, we're having A1, A2 going right to the brushes. So as the armature is rotating, it's cutting through the flux, it's producing voltage. But our F1, F2 are connected in parallel, so they are also getting a voltage around their on their coils. This is a very stable voltage, but not a lot of voltage, right? So it's going to produce. So the more load you add, it's going to be able to handle it, but it's going to still not going to have that same amount of energy that you would have with a series. But it's the stability is the important part. If you were to draw it out, it looks like this. Again, our armature is the circle, the brushes are the black boxes, and the load is straight down. And then you see that coil in the center, that's the inductor. F1, F2 is going to be in parallel with the armature. So whatever the armature creates also gets fed to the field windings. All right, so as we rotate, we're cutting through the flux. We're sending energy not only to our load, but we're also sending it through our own inductor, creating a magnetic field and allowing it to produce more flux. The flux is being cut, which is producing more voltage, and on the circle goes. Okay. Well, up to this point, we're talking about stuff that is called self-excited. So self-excited motors or generators, because they're both the same physically, they are creating their own exciter, essentially. Right? So self-excited is as the armature is rotated, it is allowed to cut through the flux. The flux is then producing voltage. The voltage is feeding its own coils. Its own coils is producing magnetic flux, which is cutting through again. It's self-exciting the same circle. So there's another option. We can have separately excited. Separately excited is when you have a battery source or another power source that is exciting, and that's the term we're going to use, exciting. We're exciting the field, and it's going to excite the field for the shunt. This is going to give us a constant, never-ending supply of magnetic flux. So that armature is spinning away, it's cutting through the flux. The flux is allowed to create that energy to produce voltage for our output. So the energy going out to the outside world is going to be direct and constant. And the more electrical load we add, the more stable it's going to be, because we are not we're not pulling the voltage down. As we add load, voltage gets pulled down. So as we get pulled more down, it's not creating the same effect that a self-excited would. A self-excited would produce a less strength magnetic field, less flux, which produces less voltage, which would starve itself out eventually. This one here has its own separately excited, so that flux is strong all the time, so it's always cutting the same amount of strength of flux. So it's very, very stable. If you look at them side by side in a graph, you can see that the self-excited, the more load you add, the more it dives down, where the separately excited is going to be a little more constant and maintained. Okay, so there's three parts that actually make up what essentially makes up what creates voltage, right? How to adjust the voltage, the three components that will eventually get to how much voltage we can produce. The first one's going to be the number of turns in the armature. Armature is the spinny part. How many times we've wrapped that coil around, right? Typically, we can't change this. This is a design issue, and so you design it according to what that voltage generator is rated for voltage-wise. So you just purchase that. The actual amount of what wrappings is producing is going to create a couple more flux, right? The more wraps we have, the more flux we are creating. More cutting, sorry. So that's going to be the amount of wraps. Something you really can't change is that the manufacturer engineer is going to do that part for you. The next part, excuse me, next part is going to be the strength of the magnetic field. This is our field, right? The outside pieces. How strong that magnetic field is. So if we have a very, very strong, very dense flux, we're going to cut through that, producing more voltage. So far we have how many times we've wrapped around in the armature, the coil. So how many wires, how many conductors are cutting through, right? And then how strong the flux is. Those are two components. The last one is the speed of rotation, how fast this thing is spinning. So the first part, again, is how many times you wrap the armature. The second is the strength of the magnetic field. And the last is how fast it's cutting. So typically, you would have control over possibly two of these. How fast it spins and the strength of the magnetic field. Because once you purchase the motor, you can't change how many times it's wrapped. That's a design issue. So that is usually a constant in most cases. But if you want to adjust the voltage, what we can do is actually put a rheostat or a variable resistor in series with our shunt winding. what this allows us to do is actually reduce how much current flows through it. The less current flows through a conductor, the less magnetic flux, right? So in this kind of application, we're assuming that the whatever is being spinning is uncontrollable. This is steam, falling water, the rotation of your engine, your car, right? The speed is constantly going back and forth, and it's not very stable. So we can't really count on that for being a variable. We also can't rewind it every time we change speeds. Every time more water comes, we can't change the way that we wind the motors, right? So that's stable. And the other one is moving around so much, it's very hard to adjust or to keep in mind, right? But the last part is going to be how strong the magnetic field is, right? The outside. If you control how many flux lines you have, you can control how much voltage you're producing. That's usually the most controllable variable of all three. So if I make a very large resistance in our shunt resistor, we're going to starve, basically, how much current is going through, and we're going to make a very, very weak magnetic field. So when it's spinning at very, very high speeds, we are producing a constant voltage coming out. If for some reason the rotation slows down, we can reduce the resistance, putting a lot of current back into the system and allowing it to create a much stronger magnetic field. And that magnetic field is now cutting, every rotation is cutting more flux so we can maintain our voltage. Something like this is called a voltage regulator. So this is something like on your car has this, and most generating systems will have a voltage regulator. So regardless of what the rotation of what is spinning the generator is doing, if it spins up or slows down, the regulator is measuring the voltage across its load, and it knows exactly what it needs to maintain at, and it's controlling how much current is allowed to flow through that shunt field. All right, so you can see here that we have increased our resistance. So what we've done is now increased our resistance where we've decreased the amount of current. So more of the current is going toward the load, but we are now have reduced the amount of voltage which we can produce because we've cut the flux lines. One of the losses in a generator and a motor, same thing, but we'll talk about generators right now. One of the big losses is going to be eddy currents. So eddy currents are a loss of energy. So if you ever go down to a river and you see water flowing in the river, and you see a rock or a boulder, and all of a sudden you see these little whirlpools happen behind the object, right? These are called eddies. Same thing happens in airplanes and everything else. As it flies, you'll see these little swirling clouds or vapor right behind the airplane as it cuts through. This is turbulence. This happens in magnetic fields and electrical fields as well, and it is a loss of energy. So instead of the energy being forced to go in one direction like that river would be, the little bit of energy is being lost in its rotation. Same thing happens here. We have all these molecules moving around with magnetic. It's becoming magnetic, and then it's not, and then it is, and it's not. You got this flow of energy and current in magnetic fields, and what happens, usually toward the ends or the corners, you're going to start seeing these energy losses or eddies. The larger the chunk of metal, the more eddies you'll create, or the larger eddies you'll create. Typically, a manufacturer will take, instead of a giant piece of metal, they'll cut metal into very, very thin slices and they'll laminate them together. This allows you to have your iron core, but it reduces the eddies because you have a thin slice of metal, so the eddies are very, very tiny, a lot less loss. So more efficient motors will have, if you look at them very carefully, they're not a solid piece of metal, they are little slits or slices of a larger block, and they're insulated between them, and they're pushed together. So that allows the eddy currents to maintain. But that is a loss of energy we have. This can be through any metals, and it creates heat. So if you ever have a generator running or even a motor running, and you put your hand on top and you feel how warm it is, those are eddy currents, right? Some is friction, some is from the bearings, but most of it is from eddy currents, the magnets and the coils switching phases back and forth. Okay. So now we're going to talk about compound motors. Compound motors have series windings and shunt windings. This allows you to have the stability of a shunt and the voltage capabilities of a series. So they're kind of the best of both worlds. They're not really great at either one, but they're kind of like right in the middle. So we have a long shunt and a short shunt. So this is the long shunt because the shunt goes all the way across, and the short shunt is going to be your shorter. It's only going to be right around the armature. One is better at overall control. So the long is going to control the overall stability of the whole system, whereas the short is going to control the stability, and it's going to be equal or take the voltage directly off of the armature. So it's going to get exactly what the armature is creating as it rotates. By changing how much the series winding gets in our field windings, it's called compounding. You can over compound, you can under compound, right? So what this means is how much current you're allowing to go through the series windings. So by doing this, we can put in parallel with the series, we can put another resistor, and we can control how much current. So like anything else, voltage and current likes to take the path of least resistance. If we have a very little resistant path, it's going to go that way and not go through our coil. So our coil has a set resistance already. So if you to make a secondary path, it's going to go through that path, and it's going to completely ignore or starve out your series windings. So it makes it very, very weak. So you get very weak, less flux, right? Smaller magnetic field. On the other side, if I make it a very, very high resistance on the secondary path, all my current is going to go through the series windings, allowing it to have a very large, strong magnetic field. So you can cut more flux. So by simply changing the resistance, I can change how strong that is. So with this method and with our creating the adjustment on our field, you can see how we can fine tune and adjust how a generator can produce voltage. We can control the series and the shunt windings now. And if you throw in a separately excited system, we can always have this very well balanced, engineered path of a perfect generator, or sort of perfect generator, a best for that application. Let's put it that way. We talked about this a little bit earlier. We're going to talk about the series and the shunt windings. The series, again, less reps, heavier gauge. The shunt is going to be many reps and a very, very fine gauge. Again, shunt is stable. Series is just a workhorse. It's going to produce a lot of voltage. Okay. And the last thing we're going to talk about is going to be our the effects that a armature has on the magnetic field. So as the field rotates, as the armature rotates, it's going to twist and manipulate the magnetic fields, getting it to rotate. So it's kind of like sticking your hand in a bucket and rolling around. You're manipulating the water, the energy inside there. Same thing happens. We've got this big chunk of metal spinning in the center. It's going to manipulate and pull the energy in a direction. Right? You got all these magnetic fields spinning. So what happens is we kind of lose our position. Remember earlier we had these perfect straight lines. These straight lines were allowed to cut the flux at 90 degrees. But if they're skewed because it's rotating, now our brushes are not set to cut through the electromagnets at the right angle, allowing it to not be 100% efficient. So we got to change that. That's called setting the neutral plane. Setting the neutral plane is actually moving the brushes mechanically to adjust for that movement. Another option is to have another set of compensating coils, which would turn on and pull it back in. So the more electrical load we add to the generator, the more this twist happens. So the more you load it, the more that twisting rotational effect happens. And these magnets, these smaller magnets, which have no effect on the actual device itself, because when they get to these little magnets, these little tiny magnets, by that time the brushes have completely disconnected from the main coil, so they have no effect on the actual generation, but they're allowed to pull that magnetic field back, and they're kind of like a steering magnet. They're going to pull it back into the right position. So the more current, the more twist, the stronger those magnets will be, and pull it back in. So you kind of get the idea how that works. And then this is just an illustration of showing that whole process, right? We have our neutral plane, we're cutting, and we have to actually move our neutral plane in order for us to cut at the right angle because of that rotation. All right, and that is it. So if you have any questions at all, please let me know. I'll be happy to help. Besides that, work on your labs, and I will see you in class. Talk to you soon.